Okay, now we are going to start a numerical problem for a conventional slab system. The statement is this one. Figure 1 shows a two-way floor systems with a total area of 12,500 square foot. It is divided into 25 panels. The number of panels have been mentioned with a panel size of 25 cross 20 fits. Concrete strength is 3000 psi and steel yield strength is 40,000 psi. Service load is to be taken as 120 psf. These are the live loads given. Story height is 12 feet. The preliminary sizes are as follow. The slab thickness is 6.5 inches. We are given with the slab thickness right now. Later on in the numerical, we will check that the given slab thickness is in accordance with the code provision or not. The other information includes the long beam dimensions are 14 cross 28 inches. 14 cross 28 means 14 is the width of the beam. This is the width of the beam. And this is the depth of the beam including slab thickness, 28 inches. For example, if this is a beam, so 28 inches mean this one. Out of 28, the slab thickness which we are given is 6.5 inches. The width here, it will be 14. So we call this one as like 14 cross 28. The short beams are 12 cross 24 inches. 12 is again the width instead of 14. Now for short direction beam it will be 12 and 24 instead of 28. In the short direction the depth is 24 inches. Overall upper and lower columns are 15 cross 15 inches. All the column dimensions are 15 cross 15. The four kind of panels, corner, long, short, edge and interior are number 1, 2, 3 and 4. Determine the total factored static moment in a loaded span in each of the four equivalent rigid frame which are designated A, B, C and D. So this is the first step in this numerical, that we will going to calculate the total factored static moment which we call as M naught. Here is the diagram for this whole statement. We have a total number of 25 panels. And we are given like on x-axis there are 5 panels of 5 bays. Each of them they are 25 feet center to center. Similarly for y-axis we have 5 panels which are spaced 20 feet center to center. So for us, like on x-axis it is 25 feet center to center, on y-axis it is 20 feet center. Both axes, x-axis and y, they have the same number of bays or same number of panels, like 1, 2, 3, 4 and 5 number of panels with 25 feet center to center means like this is 25 center to center, again 25, again 25, and the total makes 125 feet on x-axis. When you calculate 5 at 20 feet, it means 5 number of bays on along y-axis at center to center spacing 20 feet. Like here distance is 20 feet, so 20 20 20 multiplied by 5, it will gonna have a total up to here as 100 feet. The first step is to mark the rigid frames. Now we will mark the center lines and identify the equivalent rigid frames A, B, C and D. As we have already discussed, that the rigid frames running along x-axis in this directions, along x-axis they are considered as A and B. We will refer them as A and B in this numerical problem, and the one that are running along y-axis, these are referred as C and D. Out of this A and B, this will be the interior rigid frame and the rigid frame B will be the exterior. Among the rigid frame that are running along the y-axis, the equivalent rigid frame C will be, this will be the interior rigid frame, and this D will be the exterior rigid frames. The formula to calculate the total factored static moment is M naught 1 by 8 WU into L2 into Ln square, where WU is called total factored load and we have the formula for this one as 1.2 dead loads plus 1.6 live loads. The other factor here, these are L2 and Ln. L2 means center to center transverse span and Ln means longitudinal clear span. So now we will look at how to calculate the total factored load. Here in this numerical problem, the factored load Wu, it is equal to 1.2 dead loads plus 1.6 live loads. Here the coefficients are 1.2 for the dead loads, and for live loads these are to be replaced with 1.6 live load. The example is taken from the old version of the codes. Previously these coefficients were 1.4 dead loads and 1.7 live loads, but in the new revisions of the code these have been revised and we have to replace 1.4 with 1.2, means the dead load coefficient is 1.2 and live load coefficient is 1.6. So in the dead loads we have the self weight of slab, because we have given that the slab thickness is 6.5 inches. So you will convert this self weight of slab into area load. So we will going to multiply the density of concrete with slab thickness. What we are doing here, we are multiplying the thickness of slab multiplied by density. So thickness of slab is 6.5 inch. You have to convert into feet. That's why 6.5 inch divided by 12 multiplied by 150. 150 is the density of the concrete, plus 1.6 into live load. This is the live load which is given in the numerical, 120 PSF. This is already given in PSF. Because this load was in PSF, that's why we have calculated the dead loads or the self weight of this slab also in PSF. So the total factored load, it is coming out to be 318 PSF for this numerical. You will have a slightly low values because actual coefficient you will use in your numericals for dead load is 1.2 instead of 1.4, and for live load you will gonna choose 1.6 instead of 1.7. Now we will going to calculate the total factored static moments for, first of all, for the rigid frame A, then B, C and D. Just for information, like once you have calculated the total factored static moment for rigid frame A, then for the rigid frame B it will be half of the total factored static moment as calculated for the rigid frame A. Therefore you don't need to repeat the calculation for the rigid frame B and rigid frame D. The value of rigid frame D will be half of the equivalent rigid frame C. So now let us look at how you can calculate for the rigid frame A. This is 1/8 into WU. WU is, we have calculated 318 PSF, so you are converted into KSF. 318 divided by 1000, so you are gonna get KSF 0.318 KSF. L2 into Ln square. What is the value of L2? Because the rigid frame A is running along x-axis, as we have discussed. See, this is the rigid frame A. This rigid frame A is running along x-axis. So L2 for this one is this dimension. Like you will see L2 here, and this will be L1. These are the longitudinal. L1 will be the longitudinal and L2 will be the transverse center to center span. So we are given that this dimension center to center is 20 feet. So for rigid equivalent rigid frame A, L2 will be 20 feet. And what is the value of Ln? Ln is clear longitudinal span, because the rigid frame A is running along x-axis. So you have to, Ln will be this dimension but in clear span. So the center to center span here is 25 feet, and you have to subtract half column from here and half column from this side. Now let us see how this has been calculated. See, the value of L2 is taken as 20 feet. and for calculating the value of Ln 25 feet minus 15 by 12, because I told you like we have to subtract half column dimensions. For example, I just want to explain you like this one. The center to center dimension for us is 25 feet, which is kind of L1 for us, but we need Ln, which is like this one. This will be Ln, longitudinal clear span. So what you need to do is you need to subtract half dimension from here, half this dimension of column, and half dimension of this column. So overall Ln will be equals to 25 feet minus, because we are given that the dimension of these columns, these are 15 by 15, all the columns they are like 15 cross 15, 15 cross 15 inches. So half of 15 inch from here and half of 15 inch from here. So overall you have to subtract a total of 15 inches. So you will write here 15, because you cannot subtract inches from feet, you have to make it consistency. So we'll divide it with 12, and this will be the value of Ln. I hope this is clear. Look at the formula, because sometimes the students are just writing Wu into L2 into Ln. So there is Ln square, so you need to take the square here. So once you multiply all these factors, the value will come out to be around about something 448 feet kips. This is the moment, total factored static moment for equivalent rigid frame A. So now for equivalent rigid frame B, because you can see in the figure equivalent rigid frame is basically half of the equivalent rigid frame A. So the total factored static moment will be half of this one. So you just need to divide 448, this value, you have to divide 448 with a 2, and you will gonna get 224 feet. Now let us see how you can calculate the total factored static moment for rigid frame C, because now the rigid frame C is running along y-axis. So 1 by 8 is the same, Wu is fine, it's the same again. So L2, I'm just going to explain you with this here something. See here, now the equivalent rigid frame is running in this direction along y-axis. So all this direction, it is, these are longitudinal, and all perpendicular, these are transverse. So we need to find L2 for this equivalent rigid frame C, which is running along y-axis. This will be L2, like center to center dimension here, or maybe center to center dimension here, which is given us 25 feet center to center. And for this Ln means clear longitudinal span. So because this is longitudinal direction for us, for this rigid frame C, for rigid frame C and D, this is the longitudinal direction. So the clear span here will be this. I need to subtract one column dimension from 20 feet. So here what they did, like for us L2 will be 25 feet. See, L2 will be 25 feet, and Ln will be 20 minus 15 by 12 into square. So this is the total factored static moment for the rigid frame C. For frame D, because this is half of equivalent rigid frame C, so we'll just divide it by 2 and get this value, 349 divided by 175. The next step is to calculate ratio of flexural stiffness of longitudinal beams to slab. The term flexural stiffness is basically the product of modulus of elasticity and moment of inertia. So we have to calculate the ratio of this EI of beam to EI of slab. For this we need the moment of inertia of beams and moment of inertia of slabs. Now, because this is not as simple as to calculate the moment of inertia of a rectangular beam, where we had the formula I is equal to bh cube by 12, because the beams right now, they are no more rectangular, they are T-beams, because the beam is having a certain part of slab in itself. So we need to first calculate the B effective, like what is the width of which is contributing or which is acting as beam, and then we will modify the formula for calculating the moment of inertia, which is I equal to bh cube by 12. So we had to multiply it with the factor k, so that we need to upgrade the moment of inertia. As you can see in the figure, that if it's a rectangular beam, the moment of inertia would be the hashed area. Now, because it's not a rectangular beam, it's a T-beam, so I need to add this one and this one as well. So moment of inertia of a T-beam is more than moment of inertia of a rectangular beam. That's why we have to multiply a factor k with the normal formula bh cube by 12. This is the factor k. Later on we will see how we can find the value of k. The slide is basically showing the definition of the column strip and how you can find the dimensions of a column strip. So the code says that the column strip is defined by a slab width on each side of a column center line. Like, you have to first mark the column center line, and from each side of this column center line, the column strip will be 1/4 of the smaller panel dimensions, or we can write it as like 0.25 of L1 or L2. Similarly, the middle strap, it is basically defined as the portion of the panels between the column strips defined. So I'm just going to explain to you in this figure. So first thing what you need to do is you have to mark the column center line. This is the column center line. You can see from here the red line. So the column strip will be existing on each side of this. Like, this is one side and this is the other side. So the code says like this dimension and this dimension, this is basically equal to 0.25 of L1 or L2, whichever is smaller. Like, the overall this dimension, column strip dimension, will be basically 0.5 of L1 or 0.5 of L2, whichever is smaller. The rest of the dimensions, they are part of the middle strip, so you need to divide it in two, and this will be a middle strip and there will be another middle strip. This is for any interior rigid frames. This slide is basically showing a three-dimensional view when column strip and a middle strip is formed. So all this is the interior rigid frame. So in the interior rigid frame, you will have this column strip here, then a half middle strip here and a half middle strip here. And for an exterior rigid frame, you have this column strip here and a half middle strip here. So you need to distinguish between exterior and interior rigid frame. An interior rigid frame is having a column strip and two adjacent half middle strip, whereas an exterior rigid frame, it is having a column strip and one half middle strip. This slide is basically showing you an example how you can calculate the dimensions for the column strip and middle strips. So just look at here. Start from the simple case, like red line, these are showing interior rigid frame. However, in the upper figure you can see there is another red line which is showing an exterior rigid frame. So in the interior rigid frame here, the interior rigid frame is having this column strip which is shown with this yellow bounded area, like this one. This all is a column strip, and outside this one and this one is half middle strip. So the dimension of this column strip, we will calculate this one first, because the formula is 0.25 of L1 or 0.25 of L2, whichever is smaller. So now let's see how it works. 0.25 of L1, the value of L1 for this panel, because this is running in X direction, so L1 will be equal to 25 feet. 0.25 of L1 or 0.25 of L2, because the rigid frame is running in this direction, so all these dimensions are L1, and these dimensions, these in this direction, these will be L2. So here the L2 is 20 feet. So once you multiply, you will get here 6.25, and here you will get 5. So which one is smaller? This one is smaller. So you will have 5 feet here and 5 feet here, because in the definition it was stated that from the center line of the column strip is existing on each side. So 5 feet here and 5 feet here, the total column strip will be now 10 feet. So as we now know the dimension of this column strip, so we can easily find the dimensions for the middle strips, because the total rigid frame A from here to here, this is equals to 20 feet. Total width of frame is 20 feet, and out of 20 feet I will gonna subtract 10 feet. So the answer is 10 divided by 2, so you will have 5 feet of middle strip on each side. See, 5 feet middle strip on each side. Now let us look at a complex situation where we have to find the width of the column strip and middle strip for the exterior rigid frame. Consider this example where we have the spans going on 25 feet in x directions and 20 feet in y directions. So before you find the width or dimensions of the column strip, you need to find the overall width of the equivalent rigid frame. In order to find that, you have to cut the center lines, because this rigid frame, it is running in x direction, so ultimately you have to cut like these center lines in the buildings, the one I shown here, so like this one, and like this one. So the distance from this to this will be the equivalent rigid frame width, which is quite clear from this example that it is 20 feet, because the span dimension, if you can see here, these are the span dimensions here. This is 20 feet. So the total width of the rigid frame will be 20 feet. Now because this is an exterior rigid frame, not an interior one, I'll explain how we have find the dimensions of the equivalent rigid frame for this exterior frame. For example, this is a column here. Just make it like this one. I'll draw the center line connecting the columns. So this dimensions. So we have normally columns going on here, and then a column here as well. Just for this is here 25 feet. It's like, and this dimension is 25 feet, and when you go here, the dimensions of the spans are 20 feet for this point. I'll just mark the center line again for this point as well. It's the center line. These are the column center lines. So you have divided the rigid frame like this one. This is the center. So the dimension of total rigid frame for this exterior is this one. I'll just mark it with a blue color. This will be from here, that goes from here, and keeps on going on. So I need to consider two dimensions here. One is this one, smaller, and the other is this one. This is, I'll just make it one, this is the second. So sum of these two things will be the total rigid frame here. The part 2, it can be easily found, because we know that because this is 20 feet here, so this will be half of 20 feet. So 2 will be equals to 20 divided by 2, and it's equals to 10 feet. And for considering the dimension 1, because it is the half the dimension of the column. Columns are like 14 cross 14. So the first dimension, it will be equals to half of 14 inches, because it's in inches. I'm just going to convert it into feet by dividing it by 12. Now it will be equals to 0.58 something, 0.58 feet. So the total dimension will be 10 feet plus 0.5 feet, which is equals to 10.58 feet. So this is the dimension of the exterior rigid frame. The second step is to find the width of the column strip, which we already discussed. It is 0.25 of L1 and 0.25 of L2, whichever is smaller, but now because it is an exterior rigid frame, so you have to add also the half width of the column, as we have already discussed that this is an interior frame and this is an exterior rigid frame. So now let us look at the calculation. Now we have the total width. So the column strip width can be found, as we have discussed. It is equal to 0.25 of L1 or 0.25 L2, whichever is smaller. For this rigid frame, because it is running in this direction, x direction, all the dimensions along the x-axis, they will be considered as L1, and all the dimensions which are parallel to y-axis or along y-axis, they will be L2, center to center dimensions. So it is quite clear, because L1 is greater. The value of L1 here is 25 feet, whereas the value of L2 from this to this, it is 20 feet. So L2 is comparatively less, so we're going to choose this one. So the formula is 0.25 of L2. So once you make 0.25 of L2 or 0.25 of 20, the answer is 5 feet. But this is not the column strip width. I'll just explain you, because the answer is not this one. This is not the accurate answer, 5 feet. The column strip width is a little bit higher than this value. I'll explain. Okay, this is the column. Going on something here. So the definition, because this is by definition, the column strip is basically the distance from the center line of the columns, like from this center line to this place. It is 0.25 of L1 or 0.25 L2. So distance from here, from this point to onwards, for us it is 0.25 of L2, as we have already discussed, and we calculated it to be 0.25 into 20, and the answer was 5 feet. But this is not the column strip. The column strip is not this one. In fact, this is including this one for exterior frame, particularly for exterior frames. Just remember, like if we have an interior column, like this is an interior column, so you have 0.25 of L1 or L2. here, and also similarly 0.25 of L1 or L2 in this direction. And overall the column strip here, it becomes something like, if I measure it completely, then it overall becomes 0.5 of L1 or L2, whichever is smaller. This is all for the interior frames. How when you're dealing an exterior frame like this one, this is an exterior rigid frame, so the dimension from this center line to this is 0.25 of L1 or L2. It's okay, but now you have to consider this portion as well, the one I am highlighting right now with the red color. So actually the column strip width will be equals to, like, I need to include this dimension as well, which is the half dimension of the column. For this particular example, the one I'm showing you right now, the column dimensions are like 14 cross 14. So your column strip width will be now this 5 feet plus add half dimension of the column, because the column dimension is 14 inches. First you have to convert into feet, so 14 divided by 12, this will be converted into inches, and you have to consider the half dimension of this one, so divided by 2. So this will be the overall dimension of the column strip. Now let us look at the example. See, now the column strip dimension here, it is shown as 5.58 inches. The first step is to find the dimensions of the rigid frame. The second is to find the column strip dimension, and how you can find the middle strip. Last one is to find the middle strip dimension. It's easier because you know the total width. So once you subtract the column strip dimensions from the total width, so you're gonna get the middle strip dimension. Now let's move on to the next step, where we have to find the B effectives for the beam. First thing we need to know, like, the beam we are going to consider, either it is a T-beam or an L-shaped beam, because both of them, they have a different formula to calculate the value of B effective. Normally we have discussed, like, whenever you are given the dimensions of a beam, like if it's a 9 cross 15 beam, it means 9 is the width, which is width of the web, same thing. In 15 inches, it is the overall depth of the beam, including the slab thickness. So there is another dimension, which is B effective, what we have discussed in case when the beams and slabs are cast monolithically. So a part of the slab, it will start acting as beam. So what part will be, it is B effective. So we need to find B effective. So we have different formula to calculate B effective for a T-beam and B effective for a L-shaped beam. Whenever you are going to analyze beam which is lying in interior rigid frame, it will always be a T-beam, and if the beam is a part of exterior rigid frame, it will be a L-shaped beam. Means all the beams which are located at the periphery of the buildings, they are L-shaped beams. Let us have the formula for these one. The next slide is basically showing both the kinds of beam. This one is an L-shaped beam and this is a T-shaped beam. They have the different formulas to calculate the projection. This is basically called the projections. This portion, this is called the projection. So a T-beam, it has 2 projections, where an L-shaped beam, it has 1 projection. So we have these formulas. I'll just write for you these formulas. For a T-beam, like if it's a T-beam, maybe a beam which is lying in interior rigid frame, we have the formula that B effective will be smaller of two things. First is BW plus 2 times H minus T and the second is BW plus 8 times T. Here BW is the width of web, H is the overall depth of the beam including the slab thickness, and T is the slab thickness. However, if you have L beam, then B effective will be smaller of two things, BW plus H minus T, or BW plus 14. So you need to first identify what is the type of the beam you are analyzing. Depending upon either it is a T-beam or L-shaped beam, you will select one of the two formulas. Either it will be this one or either it will be this one. Once you have determined the B effective, the next step is to find the value of K, because moment of inertia for T-beam is always greater than moment of inertia of a rectangular beam. So a normal rectangular beam, it has a formula BHQ by 12, but because it's a T-beam, so you need to multiply a factor K with this one in order to convert it to a formula for calculating moment of inertia for a T-beam. So we're just going to use this formula to calculate the moment of inertia of T-beams. In this formula, BW is the width of the web, H is the total height of the beam as shown in here. So in order to calculate the value of K, we have three different procedures. Either you can use this long formula to calculate K. This is the second method. You need to find two ratios, BE over BW and T over H. And depending upon that, you are going to select a particular value of K. For example, your BE BW is 3. I'm just going to make like if it's 3. And your T over H is like 0.7, so you're going to go in direction this one. And if your T over H is 0.7, so this is your value of K. So maybe you have to do interpolation in between 2 and 3 sometimes here, and sometime an interpolation between 0.3 and 0.4. Maybe your value is 0.35, so you have a value somewhere lying in between there. So you have to do simultaneously interpolation in horizontal and vertical direction for this method. There is another third method, which is using this graph. In the same way, you need to find BE over BW and T over H. So this curve is basically for BE over BW 4, this is for 3, and these values here on the horizontal axis, these are T over H. So depending upon that, we're going to select a particular value of K. I would suggest you to find the value of K using this formula, because in the exam part, you can have this one in your design aids. So it will be quite easy and it will give you accurate values. I'm just going to explain this one. For this, you need one is B effective, then BW, then T, and the fourth one is H. These are the four variables you require to complete calculation for finding the value of K using this formula, where B is the B effective width, which we already discussed for calculation of T-beam in rectangular beam. BW is the width of the web. Here T is the slab thickness, and H is the overall thickness of the beam. We're going to do some exercise to find the value of K using this formula. In case, because in the exam maybe you have some shortage of time, so you can use these values, this one as well, this procedure, this tabular one as well. This is quite simpler, and it will give you, just for your information, if your values of K are like 1.56 and you're using this particular method, and this method is giving you a value of like 1.45 instead of 1.5, you're getting 1.4 because you didn't do the interpolation very accurately, so it won't affect your calculation or the results as much. So Don't worry about these one, just keep going on. However, if the required value is like 1.5 and you're using this table, or you're calculating it to be like 8 or 10, then it's a wrong calculation. So now this is the examples for the two-way slab beams. This is basically the continuation of the previous example, because in the first step we have calculated the total affected static moments m0. Now we are moving towards the second part, where we have to find the ratio of the flexural stiffness of beam to that of slab. So the statement says, for the two-way slab beam design problem, compute the ratios alpha of the flexural stiffness of longitudinal beam to that of slab. What is the flexural stiffness? We have already discussed. This is the product of E and I. So alpha is basically equals to EI of beam over EI of slab. In equal rigid frame, all the beams around the panel 1, 2, 3 and 4. So referring to this figure, first we will do the calculation for the B1 and B2. We have just nominated these beams as B1, B2. As you can see, these are the interior beams, B1 and B2. Similarly, if you look at B3 and B4, these are the exterior beams. However, we have repeated this one again here. You can see it is B1 again here, B2 again here, because this is continuing, it's not ending here, this is a continuation here. If you remember the overall question, which has 25 panels, the panels are going in this direction, they are going in this direction, it is repeating. However, this is the end, it's nothing here and nothing here. So B3 and B4 here in this figure, these are basically exterior beams, or the L-shaped beams, and the B1 and B2s, these are T-shaped beams. First thing, we're going to calculate the B effective, because you cannot compute alphas until you don't have the values of B effective for these beams. So we will do an exercise here to find the values of B effective for both T beams and L-shaped beams. If you remember, in the statement it was given all the beams that are in the long direction, because we have two directions going on here. One is this one, which is 25, 25, and the other one here, it is 20 feet, 20 feet. So this is the smaller dimension and this is the longer dimensions going on. So it was given that beams, either they are T-shaped beams or L-shaped beams, whatever, the one which are running in the long directions, they will be 14 cross 28. These are the dimensions of the beam, 14 cross 28. And the one which are running in short directions, they have the dimensions 12 cross 24. So we're gonna do some calculations for B1 and B2, because these are T beams. So we have the formula there, that it is smaller of the two values. First one is BW plus 2 into H minus T, and BW plus 8 into TF. So we're going to calculate this one. The beam is 14 cross 28. Just for your information, I'm just going to draw it. 14 cross 28. And the slab thickness, it is given as 6.5 inches. So 14 cross 28 means it is the width of the beam and this is the depth of the beam. So I'm just going to draw a T beam. So this is the slab thickness, which is 6.5 inches. This is the width of the beam, which is 14 inches. And this is 28 inches, which is the overall depth. We will gonna name it this variable as T. I'm gonna name this variable as H. I'm gonna name this variable as BW. And the last thing which is required here is B effective. So we're going to do the calculation. The formula is, you have to select a smaller value from BW plus 2 into H minus T. The first thing is BW. What is the BW? 14 plus 2 into H minus T. 2 into, what is H here? 28. minus T, with T 6.5 inches. The answer is 57. The other factor was BW plus 8 into TF. So again, BW is 14 plus 8 into TF, 8 into T, where the thickness of slab is 6.5 inches. And the result for this one is 66. So the smaller value out of these one will be 57. So you're going to say B effective will be equals to 57 inches. In the same way, if you are going to calculate the B effective for an L-shaped beam, so the formula is a little different. So we have done calculation for B effective for B1, B2, which is an interior T beams, and we calculated 57. In the same way, there is a beam B3, B4, which is also running in the longest span. So again, you will going to consider here 14 cross 28 beams, and both these two beams, because these are running in shorter dimensions, so these are 12 cross 24. So there will be just difference in formula for calculating a T beam or L-shaped beam. The rest will be same. So this slide is basically showing calculation for B effective for T beams and L shape. We have covered one, so you have to do the rest of these three. Just compare your values. Once you have determined the value of B effective, so you are now able to calculate the value of K. So use the bigger equations, and in those equations you need these variables. First calculate BE over BW and T over H, and then use these values in the formula to calculate the value of K. For our numerical, the beam which we already solved is a 14 cross 28 beam, and we have find these values like B effective for this beam was 57. So BE over BW, BE is 57, BW is this 14 inches. So in order to calculate the value of K using that bigger equation, you need to have these two information, B effective over BW and T over H. So we have covered the calculation for calculating B effective for a T beam. The beam was 14 cross 28 inches, and the B effective what we calculated for this beam was 57 inches. So we'll calculate these two ratios, B over BW. BE for this beam we already calculated 57. BW is this one, and for T over H, T is the slab thickness which is given in the numerical if you read the statement, and H is the overall depth of the beam, which is 28 inches. Just make sure when you are designing the beams in longer dimension, this H will be 28, whereas when you are designing the beams in shorter direction, the beams are not 14 cross 28, they are 12 cross 24. So based on this one, the value of K calculated was 1.744. So now you are able to calculate the modified moment of inertia for this T beam. So the formula was IB is equal to K into BH cubed by 12, where the value of B is 14, H is the depth of beam 28, BH cubed by 12, and this is the value of K you already calculated. So multiplying these three factors, you're going to get the value of moment of inertia for the T beam. Now let us look at the calculation for moment of inertia for the slab. The formula to calculate moment of inertia for slab here, it is again same, IS is equals to BH cubed by 12. Here H will be the slab thickness, not the beam thickness, because you are calculating the moment of inertia for slab. So H will be 6.5 inches. Now let us look how you can find the value of B. Now the rigid frame A, it is somewhere here. I'm just going to make it something, this one. This is the rigid frame A. and this one, the one hashed in a different direction, this is rigid frame B. So for rigid frame A, the width B in that formula, the one we have discussed, that moment of inertia is equal to IS equals to BH cube by 12. So the value of B, which is the width of the slab, you can see it from here. This is the width. Because beam B1 and B2, it is lying in rigid frame A, so the width B for this one will be equals to 20 feet, and you're going to convert this 20 feet into inches by multiplying with 12. However, when you are calculating the moment of inertia for slab for the beam B3 and B4, for these beams, because these are lying in the exterior rigid frame, the width will be this one, which is 10 feet. So for B3 and B4, when you are doing the calculation for B3 and B4, the value of B will be equals to 10 into 12. This will be 10 feet. So this is the concept for calculating the value of B, which is the width of slab. So for rigid frame A, the total width will be taken, and for rigid frame B, it will be taken half. Coming back to here. So moment of inertia for slab, it is now equals to 1 by 12 B into H cube, where this B is basically coming from 20 feet, because the width was 20 multiplied by 12. So you want to multiply these two, you will get 240, and 6.5 inch, this is the slab thickness. So this is the moment of inertia for slab. Now because you have the I values for beam and I values for S, you are able to calculate the alpha, which is not tough thing. You have to just divide. It's basically just a ratio. EI of beam, and in the denominator you have EI of slab, because this is the same, so E will gonna cut. So you're just gonna put here the moment of inertia for the beam, the modified one, which we have calculated using the formula K into BHQ by 12, and this is for the moment of inertia of slab coming from here. So the value of alpha is 8.27. So in the figure, you're going to see in front of B1 and B2, you're going to see here the value is written as 8.27. So now because this is a T-beam and this is also B1, B2, so all of them, they will have same value. In the same way, all these beams except the last beams, which will be the exterior beam, because they have a different shape. They are L-shaped, and these are T-beams, so they have different value of B effective and a different value of alpha. In the same way, you will going to calculate the value of alpha for these L-shaped beams, because these are B3 and B4, so the calculations are being done here, B3 and B4 for you guys. Just for your information, when you are calculating the moment of inertia of slab for B3 and B4, because this is lying in the exterior rigid frame, so this 120 is basically coming from 10 multiplied by 12, where 10 is the width of the beam, which we have already discussed. Now because we have calculated the values of alpha, which is the flexural stiffness of beam to flexural stiffness of slab for each of the T-beam and L-shaped beam in this numerical. Now the next step is to move towards finding minimum slab thickness for deflection control. As we have studied that we basically do have two kinds of slabs, one with beams and one without beams. The one without beams, they are classified as flat slab and flat plate slab systems. So if you are dealing with slab with beams, you have certain equations from which you can check the minimum criteria of slab thickness. And in case if you are dealing with slab without beams, you have to consider this table, which is specifically for flat slab and flat plate slab systems. In this column we have different values of Fy. This particular one is for slab without drop panels, mean it is flat plate slab systems, and this particular, the other one, it is for slab with drop panels. Drop panels mean flat slab systems. We have studied two different kinds in in the initial slides. First was the flat slab, which is having a drop panels and column capital. The other was flat plate slab system, which is having a thick slab resting directly on columns. Under each of them, you have exterior panels and interior panels. Like if you are finding criteria for exterior panel, then you will consider these things. And if you are considering interior panel, then this is the formula to calculate the minimum criteria: ln by 36, ln by 33, ln by 31. For exterior panels, you may have an option like they would have either edge beams or they would not have edge beams. So depending upon the inputs you are given, you have to select a particular cell from this table, and the cell will give you a criteria or equation that your slab thickness should not be less than this value. For example, ln by 33, ln by 40, ln by 34. This is just a theory which is stating like what is ln, what is sn. These are the two terms that we will use in coming slides. These are the equation which I have told you, like if you are dealing with slab with beam systems and you have to check the minimum slab thickness criteria. So you will consider these equations. Out of this equation, which equation have to be used, it depends upon whether the slab is resting on shallow beams, either it is resting on medium beams, or it is a very stiff beams. So you have to calculate first the value of alpha m's. If the value of alpha m is less than 0.2 for your system, then it means that the slab is resting on shallow beams. Similarly, if the alpha m of the slab panel it is between 0.2 and less than 2, then it means the slab is resting on medium stiff beams, and you have to consider this thing. And if your slab is resting on a very stiff beams and alpha m values are greater than 0.2, then you have to consider this formula for finding the minimum slab thickness. In either case, the minimum is not to be less than 3.5 inches. What is alpha m? I'll just explain you. Previously, we have calculated alphas for beams. For example, we have a slab panel here, which is resting on beams on all these four sides. And let's say the value of alpha here is alpha 1, the value of this was calculated alpha 2, the value of alpha calculated for this beam was alpha 3, and the value of alpha calculated for this beam was alpha 4. So the slab is resting on all these four beams, and if you have to calculate alpha m, so the alpha m is basically the average of these values. This is alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 divided by 4. This is the value of alpha m. So you will first find the value of alpha m's for your slab panels, and depending upon the range, you will select one of these criteria to find the minimum slab thickness. This slide is basically explaining a specification of the code, like if your slab is resting on beams and there is an edge beam which has then alpha stiffness ratio less than 0.8, then you have to increase the slab thickness by 10%. As per the calculation of equation 12 and 13, you will calculate the minimum criteria for slab thickness, and you will further increase that slab thickness by 10% if the edge beam at the discontinuous edge is having a stiffness ratio alpha less than 0.8. Now let us look at the example. For the two-way floor system, problem 1, determine the minimum thickness requirement for the deflection control and compare it with preliminary thickness of 6.5 inches. Because previously in the start of the numerical, we are given this slab thickness of 6.5 inches. Now we will check if the provided slab thickness is satisfying the code criteria or not. So the first step is to find the alpha m for the panel 1, 2, 3 and 4. For panel m, these are the calculation. How we have calculated this one, I'm just going to show you here. From this one, this was the panel 1. So for calculating the alpha m for this panel, we have 4 different values of alphas because the panel 1 is resting on beam, this one having alpha 13.83, then the other alpha is alpha 3.55, then 8.27 and 5.96. So alpha FM for this slab panel will be sum of all these four values, the one I circled right now, divided by 4. For example, I can say alpha M equals to 13.83 plus 3.55 plus 8.27 plus 5.96 divided by 4. This is the value of alpha. Similarly, if you are considering the panel 2, so this panel is bounded by again 4 sides, 4 beams. So the alpha will be the sum of 13.83, 3.55, 8.27, 3.55 divided by 4. So in this way you can calculate alpha M for each of the 4 panels. The calculations are shown here. I'm just going to see this one. So these are the calculations for panel 1. We have alpha M 7.90, for panel 2 7.30, for panel 3 it was 6.5, and for panel 4 it is 5.91. So now just compare these one with the criteria here. The calculated value of alpha M, it is not lying in this one, so we cannot use this one. Also, we have alpha M greater than 0.2 but not less than 2, so we cannot use this one. So third criteria is the one in which we are lying, because our alpha M is greater than 2. All the values what we have considered are greater than 2. See here? All the values here, they are more than 2. So the third criteria is the one which we have to consider for finding the minimum slab thickness for this panel. This was the equation for finding the minimum slab thickness. I'll just explain you what is Ln, what is Sn, because these are important and these will be required to find the minimum slab thickness here. Ln stands for longer clear span and Sn stands for shorter clear span for slab. For our problem we have a panel of 25 cross 20. I'm just going to draw it now. 25, and let's see, it's 20 here, something, it's 20 here again, 25 again, 20 here. So I'm just going to make these are the 4 panels we have considered. This was 25 feet each of them in this direction, and in this direction we have 20 feet going on for each of the panels. So this direction, it is basically the longer one, and this direction it is a shorter dimension for us, because the span in this direction it is 20 feet and this one is longer. Also in the numerical we have been provided that the beams spanning in longer directions, they are 14 cross 28, and the beam that are spanning in shorter direction, they are 12 cross 24. So all the beams that are running in this direction, this particular shorter direction, they are all 12 cross 24. For example, this one will be 12 cross 24, this one, this one, this one, this one, this one, all these are 24. However, the one with running in this direction, this one, this one, this one, this one, this one, they are all 14 cross 28. So now if we have to find the value of Ln, the longest clear span, so out of these two values, which one is longer? It's very clear, 25, so I'll consider this direction. This one is the longer one. So for me, I'm just going to put 25. But we know that this 25 feet is center to center span. Like there are columns here. We know that there are columns here at this point, at the intersection. There's a column here, then there's a column here. Similarly, the column here, column here. We have column here, everywhere. And the dimensions given in the numerical, that 25 feet, this is center to center dimension. Because This is Ln, means clear longer span, so I have to subtract the beam because I'm considering the longer clear span for the slab. So instead of subtracting now the column dimensions, I'm going to subtract the dimensions of the width of the beam from this 25 feet. Now the question is, we have two different widths of beam. One is 14 inches, another is 12 inches. So which one to subtract from 25 feet? So let's see here, because this is 25 feet. So if we want to have a clear span, so these are the beams that are inserting. These are the beams. If I'll just make a clear sketch here, it would become like this one, for example. This is 25 feet, for example. There's a beam coming here in this direction. Again, there's a beam coming here. There's a beam coming here. So I need to subtract half dimension from here and half dimension from here. The one we do with the columns. Now the same procedure has to be done with beam. So the beam running in this direction, these are basically running in shorter dimensions. So the beam here and the beam here, both of them, these are 12 cross 24. So the width I'm going to consider here is 12 inches. So the answer for Ln be equals to 25 feet minus this width, half it from here and half it from this side. So you can say you're going to subtract 12 inches completely. So I'm going to convert 12 inches to feet by dividing by 12. This will become 1 feet, 25, and the answer will become 24 feet. This is the value of longer clear span. In a very similar way, if we have to calculate the value of Sn, which is shorter clear span, I'll just consider again the same figure. This is 25 here, this is 20 feet here, in this direction. So out of these two dimensions, it's very clear that I have to consider 20 feet because I'm looking for the calculation of Sn. So Sn will be equals to 20 feet minus, because this 20 feet and 25 feet we already discussed, these are center to center span, so I have to take clear span. So what I have to subtract from 20 is beams that are coming in this direction, because there is a beam coming here like this one, and again there's a beam coming here in this direction. So I need to subtract half from this and half from this one in order to get a clear span in this direction, because both of these two beams, they are running in long direction. See, this is the long direction, this is long direction, this one is short direction. So the beams, these two beams, the one I'll highlight it right now for you. These two beams, they are running in long direction and they have the dimensions 14 cross 28. So the width I have to consider 7 inch from here and 7 inch from here, 14 inches. So the answer will be 20 feet minus 14 by 12. By 12 I have converted this inches, and the answer will be equals to 18.83 feet. So both these values have been shown here. Ln is equal to 24 feet and Sn equals to 18.83. So we're going to put all these values here in this formula, and the value coming out to be is 6.07 inches. This is the minimum required slab thickness as per the code. The provided thickness is 6.5 inches, so we are on the safe side. If the provided thickness is less than the minimum required, so we're just going to write that the provided slab thickness is not in accordance with the code and it needs to be revised. Next to this, we will consider some cases how we can do the longitudinal distribution of total static affected moments and then later on we will proceed to transverse distribution of these moments.